If S-alanine has a specific rotation of positive 14.5 degrees, and your observed rotation is positive 11.6 degrees, what is the ratio of S to R alanine in your mixture? Believe it or not, soccer fans can help us figure this out. Hey there, ninjas. In previous videos, we looked at the concept of optical rotation and, qualitatively, what an observed rotation tells you about a mixture of enantiomers. In this video, we're going to quantify that to figure out the ratio of enantiomers in a mixture. If you'd like more information about those topics, I have links to those videos in the description down below. Recall that if S-alanine has a specific rotation of positive 14.5 degrees, then the enantiomer R-alanine has a specific rotation of negative 14.5 degrees, equal in magnitude, opposite in sign. And a racemic mixture is a 50-50 mixture of enantiomers, which has an observed rotation of 0, because every clockwise rotation is canceled out by a counterclockwise rotation. If we got an intermediate observed rotation, the sign of the observed rotation told us which enantiomer was present in excess, and the magnitude of the rotation told us how far away we were from a 50-50 mixture. In this video, we're going to make that concept more precise by defining exactly what an enantiomeric excess is. We'll look at the calculation we need to turn an observed rotation into an enantiomeric excess, and how soccer fans can help us turn that enantiomeric excess into an actual ratio. So we'll start with this example. If I have an observed rotation of positive 11.6 degrees, what is the ratio of those enantiomers? If positive and negative 14.5 are the extremes, any observed rotation in between is treated as a percentage that we call the enantiomeric excess. For this example, we could almost treat it like percent yield. The enantiomeric excess will be the actual rotation that we observe divided by the theoretical rotation we expected times 100%. For this molecule, then, the enantiomeric excess is 80%. And because our observed rotation was positive, this is an enantiomeric excess of 80% biased toward the S enantiomer. So, does that mean that we have 80% of the S enantiomer and 20% of the R enantiomer? No. We need to be very clear about what the enantiomeric excess tells us. The 80% is an 80% excess over the racemic mixture. The enantiomeric excess tells you how far away you are from the 50-50 mixture. Instead, and this is the key point, the enantiomeric excess tells us that we have 80% of the S enantiomer and 20% of a racemic mixture. And it's this point right here, friends, that everybody forgets. And EE means we have 80% of one enantiomer and the rest is racemic. And remember what racemic means. Racemic means an equal mixture of enantiomers. So 20% of a racemate means that 10% of it is R and 10% of it is S. When you combine the 80% with the extra 10%, that really means that you have 90% of the S enantiomer and 10% of the R enantiomer. This is how we convert enantiomeric excess into a ratio of enantiomers. The enantiomeric excess tells us we have that much of the excess enantiomer and the rest is racemic. We need to split that racemic mixture in half and add together the two components to get the final mixture. Let me explain this somewhat differently. Imagine a stadium and two groups of fans. Today's match is played between the reactors and the separators. The total capacity of the stadium is 100%. And of course, before the game, the stadium is empty. Now, imagine two extreme scenarios. If only the reactors fans show up, then 100% of the stadium is full of the reactors fans and we have a pure R stadium. Likewise, if only the separators fans show up, then we have a stadium that's 100% full of the separators fans. Now imagine that the stadium fills evenly. 50% of the fans root for R, 50% cheer for S. The cheer of every R fan is completely canceled by the cheer of every S fan. Neither team has an advantage. There's no net cheering, there's no observed rotation, and there's no enantiomeric excess. This is a racemic mixture. Now change one thing. Suppose some of the separators fans don't show up. Now the reactors fans have a cheering advantage. We could say a 25% cheering advantage. That advantage is the enantiomeric excess. Notice though, it doesn't mean that the ratio of fans is 25% R fans and 75% S fans. In fact, that would be backwards. That would be more S fans than R fans. Let's walk through this one correctly. An enantiomeric excess of 25% means that we have 25% extra R fans and 75% racemic, both fans. And racemic means a 50-50 mixture, so a 75% racemic mixture means there's 37.5% R and 37.5% S. So the actual ratio of R fans to S fans is the 37.5 of the mixture with the 25% excess gives us 62.5% R fans and 37.5% S fans. And this is the mixture of enantiomers in that solution. If instead some of the R fans stay home and we end up with a 10% enantiomeric excess of S fans, Pause the video, see if you can work through the calculation to figure out what the ratio of R to S will be for this example. A 10% enantiomeric excess means 10% S and 90% racemic. The racemic mixture is 50-50, so that's 45% R and 45% S. For a 10% enantiomeric excess then, that gives us a final ratio of 55% S to 45% R. Remember, we're starting from the racemic mixture, and the enantiomeric excess pushes us out away from that racemic mixture. As two quick check your works, the sum total of the R and the S ratio should add up to 100%, and the difference between the two ratios should be the enantiomeric excess. 55 is 10 more than 45, which is the enantiomeric excess for that sample. Enantiomeric excess doesn't have to be complicated. It's just measuring how unbalanced the mixture is. And once that idea clicks, the calculations become straightforward. I'll see you in the next video, ninjas.
Thanks for training with us today, ninjas. Check out this other content to see if you can level up even further. As always, don't forget to like and subscribe.